we're going to have a look at transformations of functions. So what I've got here is a graph of y equals f of x. We've got a function f of x. We don't actually know the definition of the function, but it doesn't matter. We've got the graph here, and there are some key points marked on it. We've got the y-intercept, and we've got the coordinates of both of the stationary points on there. So we're going to have a look at what happens if we transform this curve. So let's just think about what we're looking at here. We're looking at a graph where the x coordinate is x, of course, and the y coordinate is f of x. So we can see from that that f of 0, here's x equals 0, f of 0 is minus 1, f of 1 is 3, and f of 3 is minus 1. That's how we've drawn the graph from the values that come out of f of x. So let's have a think about the graph of y equals a times f of x. And I'm going to first of all use a equals 2. So what's happened to these points? Let's look here at x equals 1. We know that f of x is 3. That was plotted on our original graph. But the new graph is the graph of y equals 2 times f of x. Well, if f of 1 is 3, then 2 times f of 1 is 6. So your new point is up here at x equals 1 and y equals 6. Let's think about this point here. We know that f of 3 was minus 1, but our new graph is y equals 2 times f of x. And 2 times f of 3 is 2 times minus 1, which is minus 2. So you can see that if we multiply this here by 2, it doubles the y-coordinate of every point on that curve. It has stretched the curve so that the amplitude has doubled. The amplitude is how high and how deep the curve is. Let's think about what happens if we set a equal to half. Well, the same sort of effect. We've multiplied all of those y-coordinates by a half because we're taking f of x, which was the original y-coordinate, remember, multiplying it by a half. So our new y-coordinate is a half of the old one. So where we had point B was 0.13, now it's 0.1, 1.5. We've halved the height of this. Where we had f of 3, which was minus 1, well, a half times f of 3 is going to be minus a half. So what we've done there is we have halved the amplitude of the curve. And notice that actually it still passes through the x-axis at the same points. And that, of course, is because if you double the y-coordinate of these points, it's still going to be 0. The y-coordinate of these intersections here was 0. When you double that or halve it or multiply it by anything, it stays 0. So this transformation will not change your roots here. The curve will still pass through the x-axis at the same points. Have a think about what would happen if we multiply this, if we set a equal to a negative number. Suppose we'll set a equal to negative 1. What will happen to this point? Pause the video and have a think about it. Okay, so if we look at this point, f of 1 was 3. So if we're now going to plot the point which is minus 1 times f of 1, we're going to have minus 1 times 3. So your y-coordinate is going to be minus 3. Let's look at it and see. So the y-coordinate of this point has changed. It is now minus 3 because we've multiplied f of x by minus 1. Similarly, this point, which was f of 3, which was minus 1, we've multiplied that by minus 1 and we end up with 1. So it's effectively turned the curve upside down. If we multiply by negative 1, we turn the curve upside down. Not a very mathematical way to say it, The technical term is that we have reflected it in the x-axis. If we multiply it by -2, we're still going to have that sort of upside down, but it's going to stretch as well. So transformations like that with y equals a times f of x, so taking f of x and we're just multiplying it by something, they do pretty much what you would expect. Multiplying it by a number greater than 1 will make the curve taller. Multiplying by a number less than 1 will make it less tall. And multiplying it by a negative will turn it upside down. Now let's think about what happens if we transform a function like this. We're taking y equals f of x plus d. So our y coordinate is just going to be f of x plus d. What's going to happen if we set d equal to 1? Pause the video and have a think about what will happen to this point if we set d equal to 1. Okay, let us put d equal to 1. So you can see that what's happened to this point is it has gone up by 1, because f of 1 was 3, but this new curve, the red one, is y equals f of x, so that was 3, plus 1. So that point has moved up by 1. Let's look at point C. What's happened to that? Well, f of 3 was -1, but the new curve is f of 3 plus 1, so we're just adding 1 to the y coordinate again. And in fact, that's true for every single point on this curve. Some of them do look very close together, but if you look closely, you'll see f of 4 was 3, and actually that has gone up by 1 unit as well. If you look very closely, that is an illusion. The curve has not changed shape, it's just moved up by 1 unit. And of course, the more I increase d, the further it moves up, but it has not changed shape. If d is negative, of course, the curve moves down. And again, it doesn't change shape. Your y-intercept changes because the curve is moving up and down here. Your turning points are still in the same place because your curve hasn't changed, but they move up and down. And of course, the points where the curve cuts the x-axis also change because your curve is moving up and down. So again, it does pretty much what you would expect. If you add something on outside the function here, the curve moves up. If you add on a negative value, curve moves down. So we've had a look at what happens when we do the transformations to y equals a times f of x and to y equals f of x plus d, where these changes are outside the function. In the next video, we'll have a look at what happens if we change what is inside the function. So if we change what we're putting into the function f.